Okay.
So let's get started with the afternoon session. So yeah, it's my pleasure to introduce the first speaker, Professor Daniel Halpern-Leistner from Cornell, and he will tell us about the structure of equivariant derived categories.
Okay, thanks. Oh yeah, you should turn that off if you don't speak. Okay. All right. So I've been asked to speak on a very old paper, but it's really nice to revisit it and think about how to present it in a way that reflects all the changes in my own understanding since I wrote it 12 years ago or something. And it's just particularly timely because last semester there was a special semester on non-commutative algebraic geometry at MSRI, and there were a lot of very interesting talks and conversations about this stuff, so we may be ready to return to it. So let me begin. Okay, so X is a variety with a G action. So I'll always assume the reductive. Loosely, what geometric invariant theory does, they abbreviate GIT for short. So it produces for you an open subset that's covariant, such that there exists what's called a good quotient. So, and for me, I always write my quotient stacks this way, and then the quotient space I'll write like this. But actually, for this talk, I'm going to be talking about the quotient space at all. I think this is cutting in and out. Is it okay? Okay. I'm given a very yes. Yeah. Generally, yes. What? I don't know. This isn't that much, yeah. But the ground field for this talk is C. But I mean, it could be whatever you want, really. What? Oh, it won't be a good quotient. It'll be an adequate quotient or whatever, yeah. It'll be a GIT quotient. Okay. So many varieties of interest. Yeah, you do need characteristic 0 for that. But many varieties of interest arise this way. So toric varieties, or quiver varieties. These all arise as X semi-stable mod G for some linear representation. So one of the themes of GIT is that you can start with a space that's not very interesting, like just a vector space. And when you take a GIT quotient, you get a space with very interesting geometry. And so, so the goal for this talk, I'm actually always going to focus on this quotient stack as the GIT quotient, but the goal is to compare so just, I'm not going to tell you what I mean by the derived category, but I should at least sort of say what I mean. I'm not going to define it, but this is the category of complexes of G-equivariant coherent sheaves, and then you invert quasi-isomorphism. Okay, so that's the goal of the talk. The first topic is actually just kind of a pure algebra topic, which is local cohomology. Oh, and it arises very naturally here. Basically, if you're trying to compare an open subset, sheaves on an open subset, like this is, with sheaves on X, local cohomology naturally appears. So I'm going to work out the simplest example possible. So, yeah, so, well, sort of in general, if you have an open subset, and if you call X the complement, then you have local cohomology, which is defined by an exact triangle. So this is the local cohomology complex. It's the fiber of the map from the push forward of the restriction of F to the open subset. And one way to think about what this is doing is, so sort of in this triangulated category, there is a map from this to this shifted by 1, but there are no maps from an object that's theoretically supported on S, which this is. So this morphism becomes an isomorphism after restricting to U. So this is sort of in the kernel of the restriction functor, and there's no map from this to that. So what they call this, usually in a slightly different context, but you can think of this as a semi-orthogonal decomposition. This time I'm talking about the unbounded derived category of quasi-coherent sheaves. So I guess, yes. So what this notation is saying is that every object in my big category here can be written as a functorial extension of an object here by an object here. And furthermore, it's saying that Homs only go this way. So there are no R Homs in the other direction. And furthermore, this is actually equivalent to DQC of U itself. So if I'm content to work with large categories, there's a very clear relationship between the derived category of the semi-stable locus and the derived category of X, namely you just push forward and that's a fully faithful embedding. But there are lots of things that you want to do with small categories. So for instance, like these categories, the big categories don't really have interesting K-theory. They don't really categorify interesting topological statements. So I'm going to show you what you can do. So let me do this example. So if I take spec of C adjoins X, so the affine line, and it has a C star action, which gives X degree 1. So C star actions, when you translate them into algebra, correspond to gradings. So then I can basically compute so the cohomology. Oh, and I should say the origin is the ideal, is the cut out by the maximal ideal X. So the local cohomology with support on the origin is just M derived tensor product with and a shift by -1. So there's a little calculation that you can do. And now this thing, so this is, the important observation is that this is not a bounded coherent sheaf. So this has infinite dimensional cohomology. And so this kind of decomposition, this basically never happens. So if you want to compare the dB of the semi-stable locus, you're going to need a different approach. So this is unbounded, but it's sort of a union of, so I guess I should say, how did I decide to write this? Okay, so it's sort of a union of finite dimensional submodules. This thing is a union of finite dimensional submodules generated by this element x to the minus n minus 1. And so these things are bounded coherent. So this thing is in a sort of natural way a filtered colimit of smaller tensor products. So then the idea here, so this formula holds if you're working with equivariant sheaves, which would be graded modules over the polynomial ring, or it works with non-equivariant sheaves. But the idea is in the equivariant setting, there's a restricted local cohomology functor. And the idea is, well, you can just write down a formula for it. So for any integer w, I can do this. Let me just define what it is on On. So this is just the free module generated in weight n. So basically what this is going to be is I take the this local cohomology module, I shift it by n, and I take the weight greater than or equal to w piece. This one comes along for the ride. So the observation is that even though this is an unbounded, this is a not finally generated module, if I look at the piece of the module that's weight greater than or equal to w for any w, that's finite dimensional. And so, right, so because all you have in here are higher and higher negative powers, of x. So this thing, so I mean, just to make it explicit, it's 0 if w, yes, what was it? Oh, yeah, 0 if w is greater than or equal to n, and otherwise you can, there's just a formula for it. Sorry, this is too low. Okay. Oops. And this is if w is less than n. So it vanishes on some of these line bundles, and on other line bundles, it spits a bounded coherent object. And you can check that this actually extends to a functor from the whole equivariant derived category to itself. Yeah. Do you want me to? I'll stay high. I don't think it's so important that I rewrite that formula, though. You could just take my word for it. There's just some explicit formula. So in this case, I'll call it, it's a theorem. So it's a theorem that this restricted cohomology functor, so it's a map from dqc of c mod c star to itself, but it preserves dB. That somehow is the key that gets this whole story started, is that you have a different kind of, there's a substitute for the local cohomology functor. In particular, what it leads to is a decomposition of dB so yeah, what it leads to, if you follow, this is A1 mod GM. Sorry, some people are more comfortable if I work over a general field, and some people are more comfortable over C. So I'm really at a loss, but yeah, this is just A1 mod GM. Okay. What you get is a 3-term semi-orthogonal decomposition. And this kind of decomposition is a template for the general theory that I just wanted to illustrate. So in this case, this category is just generated by the structure sheaf, the skyscraper sheaf at the origin, twisted by n, for n less than w. And this is generated by the same for n greater than or equal to w. And then this is just generated by a single object, the structure sheaf itself, twisted by w. And so the observation here is that together, u minus and u plus actually give a semi-orthogonal decomposition of dB with supports on the origin. So if I take dB of C mod C star, this actually is just those two categories, and you also get a semi-orthogonal decomposition. And this is actually how this general thing is constructed. You use this local cohomology, this restricted local cohomology functor to get this decomposition. So basically the projection onto U plus is the restricted local cohomology functor. And then with a little bit of work, you show that actually, if you go into the big category, there is a middle component which is defined to be orthogonal. So it's defined to say that there's no maps in this direction and there's no maps in that direction. So it's orthogonal on one side to U plus and on the other side to U minus, and that is the category G. And the other important observation here, which is too silly in this case, but if I take dB of x semi-stable mod C star, so the semi-stable locus here is like the complement of the origin. So this is actually, I think studying C mod C star, you can really learn everything you need to know about stacks by studying C mod C star. So this thing is actually just a point. So this is, but the key is that it's actually equivalent under restriction to G, which is something mildly non-trivial. It's that this is an exceptional object in that category. It's not a deep fact, but anyway. So that's the theorem. Yeah. So to return to the general GIT for a moment. So basically, what you have is you have a x that, yes, as Ivan says, I'll put this inside of p to the n times am, and it'll have a g action, which comes from a linear action on this ambient variety, and I'll fix a parameter. So there's some flexibility here, but I'll think about this as L plus 2 pi I theta, and the parameter, if you're working over C, you can just say H2, but I guess I'll, the equivariant Nernst-Severi group of X tensor with C. So this L, the real part, I think of as a GIT parameter, and the imaginary part will be a shift parameter. So just like in this example, there was a GIT parameter that I hid from you. That was what told me that the semi-stable locus is the complement of the origin. The other choice of GIT parameter would say that the semi-stable locus is empty. But that's a valid parameter as well. But I hid that. But this other parameter is the W. So this is actually Z many theorems encoded because you can do this whole construction for any W. Yeah. And so then basically the general theorem is exactly this, that there exists a restricted local cohomology functor. So, let me call. Oops. So in this situation, the GIT parameter defines a semi-stable locus, as I mentioned before, and I'll just use the term S, just like before, for X minus the semi-stable locus. Okay, but just to emphasize that there's this L parameter. So there's a restricted cohomology with supports functor that takes dQc of X mod G to itself that preserves So in general, it preserves D minus co. Yeah, which the complexes with coherent cohomology that's bounded that is eventually zero in positive cohomological degree. And so it preserves D minus co, and it leads to a semi-orthogonal decomposition just like this one. So put the parameter there. So there's a super general theorem of this kind. I mean, and I should say that a comment is that if X is smooth, there's sometimes LCI. Or LCI with an extra condition that I'm not going to explain. But so then it works for dB. So this is the main theorem. What? Sorry. Oh, it works for dB co. Yeah, in general, these truncation functors in the quasi-coherent category can introduce infinitely negative cohomology groups. But there are certain conditions that you can check in practice that the truncation functors preserve dB as well. And you get a three-term decomposition. So the zeta here is encoding a dependence on L and a dependence on theta, and that's actually going to be key. Okay. I think that's all I wanted to say. Well, no, not nearly all I wanted to say, but I think that's all I wanted to say about the general theory. So this is generalized further. I mean, it works for like basically an arbitrary derived algebraic stack with what's called a theta stratification. There's a version of this theorem. So this is a very general thing. But the applications you have to get a little bit more intimate with this object. Oh, I didn't say the most important thing, that the restriction functor is an equivalence with D minus of the semi-stable locus. And these two objects together, just like before, these two objects they give you a decomposition for D minus with supports on S. Okay, so just like before, these two pieces form the entire category with supports on S, set theoretic supports on S, and this thing is equivalent to the category of a GIT quotient. So to actually apply this, you have to, in specific examples, you need to be able to say a little bit more about this category. So I wanted to focus, to show you, illustrate sort of how this gets applied. I'm going to focus on X as a smooth projective variety. And just with a C star action. So in this case, the GIT prescription is relatively simple. So I'll draw a sort of picture here. And so this is X. It's a blob. And there are certain fixed points for the C star action. They don't have to be points. They can be subvarieties. And there is a moment map for this for the S1 action that maps to R. So I'm going to put my and this is called the moment map. And basically, what GIT says is that for each of these fixed loci, I can consider the stuff that's attracted as t goes to 0 by the tautological one-parameter subgroup or its opposite. So another way to say it is I can say like sort of the ascending manifold from this fixed locus or the descending manifold. And what it says is that you should always flow away from the moment fiber. And this will give you some closed subset that's not I mean, maybe it's not obvious, but it's a closed subset, and the complement is the semi-stable locus. What's left over? Okay? And in this case, yeah, I mean, if you're in here, you just have a moment, there's just a formula for it, yeah. Yeah. Yeah, because the Kähler, it uses the line bundle. Another way to say it is that these heights here, where it hits R, the value of the moment map at the fixed points are the weights of the line bundle that you're using to define the polarization, maybe up to scale, something like that. Right. So in this case, let me just give you a sort of picture. So G is equal to the set of complexes. So this is a smooth situation, so I'll use dB, such that the weight of the restriction, let me give these names. So this Z0, Z1, Z2. So the restriction to each fixed locus has to be in some interval. Theta plus then 0 to eta I plus or minus. Is that visible? Is something, is the weight of the line bundle there. So there's an ample line bundle. I mean, if you prefer to think of this in algebraic terms, there's just an ample line bundle, and you can say what is the weight of the line bundle on each of those fixed components. And it's also the value of the moment map, up to scaling, I guess, yeah. So this is the category here. Basically, it's saying I consider all complexes in the equivariant category whose restriction to the various fixed points, their weights lie in a certain window. And here I've simplified a little bit. This is the window shift parameter here. And the L is entirely, so all of the L dependence comes in these numbers that I haven't told you what they are, but these are some integers, these eta i's. This is where the L dependence happens. Yeah, so the L dependence is in these integers. So basically, I'll say it, but not write it down. But the point is that what you do is you take the one parameter subgroup that's attracting this manifold to the fixed locus, and you take the sum of all the normal weights with respect to that one parameter subgroup. So it's always going to be some positive integer, I guess, unless the stratum is dense. But okay, I should say that there's a very interesting GIT. So the level of this moment map, the fiber that you take, you can actually take any moment fiber. It just corresponds to twisting the line bundle by a character. And maybe one of the most interesting cases is when you take a moment fiber out here, and then the semi-stable locus is empty, and what you get is just the BB stratification of the manifold. So that's an example of this phenomenon. And it's a useful case too. Okay, so basically what you could do So what you can do in this situation is you can define, I think of it as a sort of, let me just, so I'm going to tell you about various things you can do with this theorem in this setting, and they sort of generalize to the more general situation. So one thing you can do, which is like a categorical analog of the Atiyah-Bott localization theorem. So you can define a category. So this is, you can think of this as Atiyah-Bott localization. So I'll call it D hat, X mod G, and G is C star here. And this is just the full subcategory F in DQC. So it's the full subcategory of quasi-coherent complexes such that F restricted to X semi-stable is in DB. and this restricted cohomology functor for the unstable locus is in dB for all theta. So, I mean, dB lives in this category, but other things live in this category too. So it turns out that if I just take, if I push forward something from the so J lower star maps dB of x semi-stable mod C star to this category D hat. So it's not so much a localization theorem, it's more like a completion doing this procedure. But anywho, so the cool thing about this category is it's still symmetric monoidal. So it still is a ring. Its K-theory is still a ring, and its K-theory is non-trivial, and you can tell that because there's a pairing. So, you know, R hom from E to F is finite. Or E in dB and F in D hat. So if you take or in particular global sections, there's some finite dimensional thing. So this is you're adding lots of objects, but it doesn't get as bad as adding all quasi-coherent objects because you can still, there's still a well-defined index for these objects. And the theorem, one consequence of this theorem, the general theorem, is that you have the following. What? X is that. Yeah, it's smooth projective. There is a version that you can state in really grotesque generality or whatever, but I just, yeah, I wanted to be clear. So this is, if you do this procedure, by the way, like if you just take BC star and I consider complexes in BC star, basically its K-theory is like these Laurent polynomial rings, because it says that, you know, every weight space has to be finite dimensional and the weights have to be bounded below, bounded above, yeah. Weights bounded above and finite dimensional. So if you consider the category of graded vector spaces with weights bounded below that, and finite dimensional graded pieces, this is like a generalization of that. And so its K-theory is like some kind of completion of the equivariant K-theory of X. But so the claim is that in this category, you actually get the following. So I can take the class of O. So basically in K naught of D hat of X mod C star, like lots of things work very nicely. So you can take the class of OX, which is the identity, and you can write it as O of X semi-stable plus sum over I of sigma I lower star of OZI divided by E of the normal bundle. So part of the claim here is that if you do this procedure, and if you, so this, for instance, the E of a vector bundle E is like the alternating wedge powers of E star, something like that. So if you look at this object as a K-theory class on the fixed locus and you do this kind of completion operation, it's actually a unit. That's what this is saying, and actually you can, and if you invert it, it's a well-defined K-theory class on the fixed locus, and you push it forward, and it has a well-defined K-theory class in this category, and you have this. This is a decomposition into orthogonal idempotence. So somehow in this category, it's big enough that that in some sense the unit in K homology splits as a sum in one piece from the semi-stable locus. So this is just like the Atiyah-Bott localization formula, except that you might not be used to seeing this term. And so in a way, this is a refinement. So I mentioned there's a special case where you put the moment fiber all the way out there, and then you just get these things. I should say that you might wonder about different moment fibers. This completion is dependent on L. So this completion is dependent on this decomposition, which depends on the choice of plus or minus co-character at each of these fixed loci. So for different GIT quotients, you get different values of L, you get different completions, and each has a theorem like this. And so in particular, you can integrate and you get some localization theorem. So if you move the moment fiber all the way to one side, you just get a formula for the invariant index of some vector bundle on X as a sum of contributions from the fixed loci. Or if you'd like, it's also a wall crossing formula, because if you want, if I want to know what is the index, so this gives me many different decompositions of this. So it says on the one hand, this would be the index over X semi-stable mod C star, this GIT quotient, plus some correction terms. But I can apply this theorem for a different GIT quotient, and it allows me to compare the K-theoretic index of the same vector bundle. The left-hand side does not depend on the GIT parameter, but the right-hand side does. And so I can compare the integral over the semi-stable locus with the different GIT parameters. That's the flavor of what this kind of theory is used for. One application of this theory. So that's all I'm going to say about localization, yeah. There's always, it's the things that are, the things that admit a map from a perfect complex whose complement, whose cone is supported on the unstable locus and has like negative weights or something like that. There's always yeah. I mean, I don't know, it's, maybe I can talk afterwards, yeah. Oh yeah, that's VIG. That's VGIT. Yeah. So it'll change. It changes the GIT quotient. So okay. So that was the next thing I want to say. Then the other thing you could do is you can compare GIT quotients. For a different L. And from this description, you can sort of see what happens. So I mentioned varying the GIT quotient. You can think of this as just changing the moment fiber that you take. So if I choose this as my the zero for my moment map, then all of a sudden this yellow stratum, which was unstable before, becomes it flips, and it becomes unstable in the other direction, and these points become semi-stable. So now the new is this other open thing. But what happens to this description is very mild change. Basically, the width of these windows just change. This category, and that's what I said, what I meant when I said, if you want to apply this, you have to understand this category a little bit better. So in this case, this is not the description of the category that I gave you in the theorem. That was some kind of, it's left orthogonal to this and right orthogonal, but it boils down to this. And so now you can just see visually that if eta I plus and eta I minus are the same at this Z2, then this category literally doesn't change. So it's literally the same category. So the point is that if it turns out if the canonical bundle of X restricted to Zi has weight 0, then eta I plus is equal to eta I minus. And so you get the same G. And the point is that this gives you a derived equivalence. So this gives you this G via restriction is equivalent to dB of x1 semistable, and it's also equivalent to dB of x2 semistable. I'm sorry for going low again. I'll write it up here again. So this is the basic way that you get derived equivalences between varieties. But it's a pattern that many of the results in this area kind of fall into this pattern. So the general theorem is a powerful tool, but it doesn't exactly give you the. So there's still a second phenomenon that I think people who are working in this area are still trying to figure out. So that the idea is this phenomenon is somewhat mysterious. Is that sometimes this G category, is the same for different GIT quotients. So now I'm leaving the original paper that I wrote about this, and over years I've extended the scope where we've observed this phenomenon. So examples include I guess X mod G, where X is what they call a quasi-symmetric linear representation. And in this situation, there's a category where basically you say it's the category generated by OX tensor U, where the weights of U lie in some shift of a certain polytope, a zonotope, really. So my theta parameter is where I shift my zonotope, and I say I want to consider representations such that when I look at the weights that appear in the representation, this is the weight lattice. So, if theta is generic and all the weights, all the lattice points are in the interior, you just consider the subcategory generated, and it turns out that is a G, that is one of these G categories for all GIT quotients simultaneously. And so you get, this picture where you have some G that's equivalent. So this description of the category has nothing to do with L, is the point. So you get some subcategory of the equivariant category that's described, depends on theta, but not on L. And therefore, you apply the theorem with all different L, simultaneously you get equivalences. And in fact, because there's a theta dependence here, you get many equivalences. So because I could go from one GIT quotient to another with one value of theta, and then I could go back using a different value, applying the theorem to a different value of theta. And these auto-equivalences can be assembled to give representations of generalized braid groups, generalized affine braid groups. What? I don't know the answer to that. I haven't investigated it seriously, but I don't know the answer. Yeah. So the point is that these various ways to get autoequivalences, you can stitch them together, and you get a representation of this group that's predicted from string theory, from mirror symmetry, basically. But it's sort of surprising just from the perspective of geometry, because it definitely doesn't come from definitely doesn't come from geometric autoequivalences. So yeah, so basically, this is a case in which things work very nicely. Another example is if you take algebraic symplectic reduction, so the kinds of things that come up for quiver varieties, Nakajima quiver varieties, the machinery works nicely. And throwing everything I had, I was able to actually use this kind of argument to show that any Calabi-Yau that's birationally equivalent to a moduli space of sheaves on a K3 surface is derived equivalent. So I was able to prove the de-equivalence conjecture for Calabi-Yaus in that birational equivalence class, basically by using this same principle. The same principle is that you can, for two different stability conditions, you can find a subcategory that gets identified with the derived category of both quotients. So I say that the real obstruction in general is that the general description of this GS depends very sensitively on the L, almost continuously. For instance, you can't see it in the rank 1 case, but as soon as you go to rank 2, you say that the weights with respect to some co-character that's varying continuously with L have to lie in some strip. So it becomes really, really hard to compare different GIT chambers. So the thing that we're working on now is to try to come up with descriptions of these G categories that are less sensitive, that vary semi-continuously with the GIT parameter L, for instance. So I feel like if we figure out how to do that, then we'll be much closer to understanding this phenomenon more generally. Okay, I'll stop there. Thank you. Okay. Yeah. Oh, so there's a choice depending on which moment fiber you choose tells you if you should take the ascending or descending manifold, and the ascending and descending manifolds have different values of eta in general. So the eta plus, I didn't specifically tell you which is plus and which is minus, but one of them, is if you take the ascending manifold and you take the sum of the normal weights, or you can take the descending manifold and take the sum of the normal weights, and those can be different. What? I don't know. Yeah, I don't know. Yeah, and yeah. Mm-hmm. Yeah, that's a fruitful way to think of this is to kind of zoom in. Yeah, on the fixed loops, you also have a moduli space. I mean, you also have a GIT quotient. And so you can actually just throw away all the stuff that stays unstable on both sides and look at just the stuff that's semi-stable on the wall. And that's actually a fruitful way to think about wall crossing because in general, for instance, for stacks of coherent sheaves or something like that, if you're varying stability conditions, you don't want to think about the whole stack. I mean, you could if you wanted to, but you don't want to think about the whole stack. So in that situation, you have a variation of stability and you consider the semi-stable objects on the wall, and that has a good moduli space. And if you perturb the stability condition, you get two partial resolutions of that moduli space. So that's more, I would say, is the general wall crossing picture is that. It's a stack with a good moduli space, and then you consider line bundles on the stack, and each one gives you a partial resolution of the moduli space. Okay. Oh, yeah. So I think, this K-theoretic version, there's a little bit of difference in that in K-theory, it's a little nicer because you don't actually have to have a Deligne-Mumford stack. So any stack that has like a proper good moduli space, you can define K-theoretic index on it. You can take a cohomology be finite dimensional. So I remember looking at this book, and part of the challenge there is to introduce kind of rigidifying data and then show that it's independent of the choice. So you can skip all that stuff. Same, likewise with the wall crossing. You don't need a master space. You can just say take the stability on the wall, and then you get a wall crossing formula directly by varying stability on the wall. No master space.
Yeah, I have a question. I want to ask about the connection to new symmetry. So, not help to start with the real symmetry for the total space X and the real symmetry for the function. And what happens if you put everything to your side?
So that's another very interesting mystery. I mean, so like in this A1 mod GM case, the mirror is sort of looks like this. It's like the kind of the infinite comb. So people, this is like the general, this is the mirror to C mod C star. This is what people will tell you, but it's not exactly right because you have to say which Lagrangians do you take. And yeah, there's a way to say that. So there is a way, or maybe I only know how to do it in this example. But what the theorem is telling you is that you have this three-term semi-orthogonal decomposition, and you have U minus G U plus. So the claim is that in these mirrors to equivariant categories, you should always somehow be seeing this structure. And like there are two ways to see it here. You can take these kind of loops and then a single. So there's a version like this, and that corresponds to the GIT quotient that I showed you, where you have a and then there's a version where you just take these Lagrangians. And that corresponds to the semi-stable locus being empty. But the full story of this, I think, is far from being understood. And there's a lot of interesting, like Peng Zhou and shoot. Jesse, I can't, what? No, I can't remember, sorry. Anyway, there's a lot of interesting stuff being done on that question. Yeah, what is the merit to this story? But somehow it should look something like that. So I've taken a very long detour recently into bridge instability. So I mentioned that the phenomenon where you have a single G that works for all GIT quotients is very mysterious to me. So I wanted to find, are there ways to realize this decomposition that are more categorical, that don't explicitly use the GIT stratification? Because it's when you explicitly use the Kempf-Ness stratification that you get something that depends very sensitively on L. And so I had this, it's not well-defined, it's sort of not fully formed idea yet, but about like that maybe there's a path in the stability manifold that where the stable objects tell you which of these categories you lie in and stuff like that. So I've recently been developing a picture, like a general approach to semi-orthogonal decompositions that using semi-orthogonal decompositions that come from stability conditions. But I haven't had a chance to return to this yet and figure out if that